Hey everybody, welcome back to Environmental Organic Chemistry with Dr. Lisa. I'm going to go over the quiz that you guys just took yesterday and try to explain some of the answers. So first question, which of the following are true of the activity coefficient of an organic chemical in water? And I always try to note when more than one answer is possible, but there is one question later on that I forgot to do that, so I gave you some partial credit. So the activity coefficient of a chemical, an organic chemical in water, first of all, it is the inverse of the mole fraction solubility. So that is true. And because it's the inverse of the solubility, if the solubility goes up, the activity coefficient will go down, right? So that means that, okay, let's think this out. When the salt content increases, the solubility goes down, and so the activity coefficient should go up. So that's true. When the volume fraction of a co-solvent increases, more co-solvent should increase the solubility, and increased solubility would decrease the activity coefficient. So that's not true. It's a stupid concept that the authors of your textbook seem to like. That was also true, but I didn't take any points off if you didn't choose that one. Okay, which of the following is easiest to estimate? Well, it turns out that the easiest thing to estimate is enthalpy of vaporization. And if we go look at our vapor pressure lecture, we know this from here. This is the Gauss and Schwarzbach equation. And if you just know the vapor pressure of the chemical, you can very easily estimate its delta H of vaporization. Whereas the other two terms here are much more difficult to estimate. Excess enthalpy of dissolution is basically just a guess, and so is enthalpy of fusion. I mean, you can estimate this based on symmetry and blah, 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 but it's not easy. So definitely enthalpy of vaporization is the easiest to estimate. The solubility of a gas increases as the temperature decreases. This is true. I know it's weird, but it's true. Has always been true, is true of all gases, not just organic gases. So like oxygen is more soluble in cold water than in hot water. Okay, which of the following functional groups can both donate and accept a hydrogen bond? And I did my best to draw them here, but you know, that's why I also gave you a little site that you could go to show you the different organic functional groups. But the key is this one has a hydrogen. So a carboxylic acid can both donate and accept, and so can an alcohol. But the ketone does not have a hydrogen that's bonded to an oxygen or anything. They're all bonded to carbons, and therefore they're off the market. And benzene and aromatic rings can accept hydrogen bonds, but they can't donate them. So those are the right answers there. On this question, you were asked to think about delta H of vaporization, and you know, I gave you the hint here. Let's think about which of these chemicals has the highest delta H of vaporization and which one has the lowest. Okay, propane is the smallest in terms of molecular weight, which means it has the lowest van der Waals forces. It has zero polarity, and it has zero ability to hydrogen bond. So it's definitely going to have the lowest. So that's the 16 kilojoules per mole. Okay, among these three, we can guess that chloronaphthalene and hydroxynaphthalene are higher in molecular weight than plain old naphthalene, so they're probably greater. And the hydroxy group on hydroxynaphthalene gives it the ability to both donate and accept hydrogen bonds, which is going to raise its delta H of vaporization quite a bit. So hydroxynaphthalene would have the highest, so that's that 60. And then between naphthalene and chloronaphthalene would be higher than naphthalene, so that must be the next one, which is 58, and that leaves naphthalene at 43.7. So that's how you have to reason your way through this. And I will ask similar questions to this, I promise, on the midterm. I'll give you structures and ask you to estimate things like Henry's law and stuff. If you were trying to measure the biodegradation of a big hydrophobic chemical like naphthalene, I use naphthalene over and over because I wanted you guys to have a picture of it. You know what I'm talking about. You know it's a solid. You now, if you got this question right, you know what its delta H of vaporization is. So if you want to increase the solubility in water of a big hydrophobic chemical, first of all, is going to have a positive HEW, excess enthalpy of solubilization, which means that its solubility will increase when the temperature increases. So heating up the water would help. Adding sodium chloride would depress the solubility, so that's not going to help. Adding a co-solvent would work. Increasing the pressure isn't going to make any difference because we're in water, not a gas. Adding a co-solvent such as methanol might kill the bacteria, so it's not always a perfect solution, but it's technically true that it would increase the solubility of the compound. Okay, this question, I like this question. This is a tricky question, but you had to think about it a little bit. If you have a chemical and you're trying to think about its solubility at 0 degrees Celsius and 0 salinity, how does that compare to its solubility at 15 degrees Celsius and 0.5 molar salinity? And we can go to the homework that we did here, homework number 3. So here's just an example of homework number 3 for, this is for naphthalene. And so here's its molecular weight and everything. We calculated its temperature dependence, and here's the solubility of the liquid. And notice that if I take the solubility at 15 degrees and divide it by the solubility at 0 degrees, it went up by a factor of 2. And you could see that from these plots that I forced you to draw. That's why I made you draw these plots, because I wanted you to get it into your head that temperature has a huge effect on things like vapor pressure and solubility. But then over here, I made you calculate the solubility in the presence of salt, and it went down by, here's the ratio. Here's without or with salt divided by without salt, and the solubility went down by 28%. So a factor of 2 over here versus only 28% over here, temperature is a more powerful force. I was hoping you would remember that from the homework. So the answer here is, where is it? Solubility goes up because the increase in solubility caused by the higher temperature is bigger than the increase due to salinity. I gave you some partial credit for some of these other answers because I could see where you were coming from. But yeah, this is definitely the right answer for a big, large hydrophobic chemical like naphthalene. You might get a different answer for other chemicals. Certainly if it's a gas, the temperature is going to drive the solubility in the other direction. But that's why I made sure to tell you that naphthalene is a solid at both of these temperatures. Okay, for a large hydrophobic chemical like naphthalene, which of the following are true? And so this is again related back to the question about which is easier to estimate. And if we again look at some of our lecture notes here. So here's some data on delta H of vaporization. And I don't know if naphthalene is it. Yeah, there's naphthalene, 47.3. But anyway, 30, 40, 50, even maybe up to 60 kilojoules per mole. So relatively high compared to solubility here. Remember this table? A lot of these are close to 0. And even the big ones are only getting up to 10, 20 kilojoules per mole. So for the most part, HEW is going to be much less than delta H of vaporization. So enthalpy of vaporization is greater than excess enthalpy of dissolution. Which of the following statements about surfactants are true? They lower the apparent solubility of hydrophobic chemicals. That's not true. They increase the apparent solubility of hydrophobic chemicals. That's kind of the point of surfactants. Their aqueous solubility is hard or impossible to define. That is true because they form micelles, and so you can't really define it. This is the one place where I should have said more than one answer is possible, and I forgot to do that. So I gave you a lot of partial credit here. Surfactants have a nonpolar tail and a polar head. That's true. That's kind of how they work. And they form micelles in water. That is also true. Okay, and then finally the killer question. I ask this question every year and no one can answer it. And a couple of you did really well. I think 1 or 2 of you got the full 10 points here. But the hypothetical subcooled liquid vapor pressure is the vapor pressure of the chemical, even though it's in a temperature at which it would be a solid, but assuming that it never became a solid, it stayed a liquid. And therefore, you don't have to account for delta H of fusion. And that's useful because delta H of fusion, as we have seen, is much more difficult to estimate than delta H of vaporization. So you can pretty accurately estimate this hypothetical subcooled liquid vapor pressure, and you can use it to compare many chemicals with each other and leaving out the idea that some of them might have frozen into solids. And so that is important because it allows you to make apples to apples comparison amongst chemicals. And later on, we'll see that that can be used to construct prediction techniques that will allow you to predict vapor pressure and then later correct it for the fact that the compound is a solid. So it's useful for a whole number of things. And, again, some of you got a lot of partial credit here. Some of you got full credit. So that's the quiz, and I would welcome your feedback on the format and the timing. I assume that 10 minutes may not have been enough because a lot of you didn't finish. So I'm happy to hear your feedback, but those are the answers to the quiz questions.